All right, so get this. We're diving deep into the world of sound, but not just any sound, ultrasound.
Yeah.
But like way beyond those fuzzy black and white images, you know what I mean? We're talking future computers powered by ultrasound.
Sounds pretty wild.
Totally. You sent over some MIT research about, what was it called?
Acoustic metamaterials.
Yeah, those. And let me tell you, I needed to bring an expert speaker to help break this down.
It's really fascinating stuff.
So before we get too far, acoustic metamaterials, those are basically like structures that can, well, they can control sound waves.
Exactly. They can bend sound, focus it, even make it disappear.
Kind of like sound superpowers, right?
Yeah, you could say that. And what MIT's done is they've figured out how to do all that on a microscopic level using ultrasound.
So instead of like giant structures, we're talking like tiny.
Yeah, microscopic. We're talking controlling sound at a scale you'd need a microscope to see.
That's insane.
It is pretty incredible. They've basically created a framework for designing these microscopic acoustic metamaterials. Picture a 3D lattice, like a super tiny jungle gym, and then they put microscopic spheres inside it.
Microscopic spheres, okay. So these little spheres, they're the key.
The placement of the spheres, yeah. That's what dictates how the ultrasound waves move through the material.
So like move them around and the sound changes.
Exactly. Speed up, slow down, change direction. Think of it like a tiny obstacle course, but for sound.
Okay, that's cool and all, but why should I care about microscopic sound? Like, what does it mean for, the real world?
Well, think about medical imaging. Imagine ultrasound that doesn't just show you the inside, but can see with incredible precision, like down to the cellular level.
Instead of blurry blobs, you're saying we could see, like, individual cells.
Potentially, yeah. That could be huge for diagnosing and treating all kinds of diseases, especially things like cancer or neurological conditions.
No more guessing games, basically.
You got it. And there's more. What if we used ultrasound to send information inside the body?
So like data traveling on sound waves.
Exactly. Think about the possibilities for medical devices, treatments, monitoring things with incredible accuracy.
Oh, that's like straight out of Star Trek.
It's getting closer to reality all the time.
Yeah.
And then there's something even more futuristic. Mechanical computing.
Mechanical computing. We're already pushing the limits of sci-fi here.
That's where things get really interesting. It's the idea of using sound waves instead of electricity to actually do computations.
So sound-powered computers, really, wouldn't they be, like, super slow?
It's a radical idea for sure, but the potential payoff is huge. Think about it. Sound waves can travel through stuff electricity can't, like water, even the human body.
So, like, computers inside us, running on sound. Mind blown. But, okay, the speed thing.
That's one of the big challenges, yeah. We got to figure out how to manipulate those waves at super high speeds to make it practical. But traditional computers, they have a heat problem. It limits their speed and how efficient they can be. Sound waves don't have that same issue.
So if we crack the speed code, sound-powered computers could be faster and more energy efficient.
Potentially both, yeah. Plus, they could work in places where electronics just fry.
All right, so MIT is laying some serious groundwork here. But how did they actually make these tiny acoustic metamaterials? Did they just, like, toss those little spheres together?
Not quite. It was a combination of really sophisticated design and some seriously meticulous experimentation.
So it wasn't an accident?
Oh, no, this is very intentional. They used computer simulations to figure out how different sphere arrangements would affect the ultrasound waves. Then they had to build these teeny tiny structures, which is crazy hard.
Yeah, I can't even imagine building something that small.
It takes some seriously specialized equipment and techniques, like stuff borrowed from nanotechnology. They build these lattices layer by layer, carefully placing those microscopic spheres to get the exact properties they want.
So they're like building with atoms?
Essentially. And the crazy part is they proved it works. They can actually control ultrasound at this scale.
Wait, how do they prove that?
They used a technique called laser ultrasonics characterization. It's complicated, but basically they use lasers to generate and measure ultrasound waves inside these microscopic structures.
They shine a laser on it and listen to the sound.
In a very simplified way, yeah. And it proved their theories were right. They can manipulate the speed and direction of those waves just by changing how those tiny spheres are arranged.
Okay, I'm following so far. But what did they actually do with these, what were they called?
Acoustic metamaterials.
Right, the metamaterials. What did they actually build?
One of the coolest demos was an acoustic demultiplexer. A demultiplexer. Think of it like you have a cable carrying a bunch of signals, like a fiber optic cable for internet. A demultiplexer splits that signal back into its separate parts.
So it's like a signal traffic cop sending everything to the right place.
Exactly. MIT built one for sound waves, and they did it at this microscopic scale. It can take one ultrasound signal and split it into multiple signals, each with its own information, all in a space smaller than a hair's width.
That's insane. What can you even do with that?
Well, think about it. Signal processing, handling huge amounts of data in tiny spaces, or in medical imaging, you could use different frequencies to see different tissues at the same time. The possibilities are really vast.
All right, my brain is officially fried. So we've gone from big sound to microscopic sound, but where do we go from here? What are the big hurdles left to jump over?
Well, one of the biggest is scaling up. Right now, this is all tiny. To make it practical for, medical imaging or computing, we need to make these metamaterials way bigger.
So from micro to macro.
Exactly. That's going to take some clever engineering, new manufacturing breakthroughs, that kind of thing.
Okay, bigger. What else?
Complexity. The bigger these metamaterials get, the more complex the design becomes, and that's a challenge too.
So bigger and more intricate. Got it.
Mm.
I am still stuck on that sound-powered computer idea, though. It just seems so wild.
It is pretty wild. I mean, who would have thought that the same tech we use to see babies in the womb could lead to a whole new kind of computer?
It just goes to show that sometimes the biggest discoveries come from the most unexpected places. But, okay, before we get too carried away dreaming of the future, let's circle back to this MIT research and make sure we understand what they did.
Sounds good.
Okay, so they've made this sonic toolbox, right? They can control ultrasound in pretty much any way they want. Speed, direction, split it up, all that, all at a microscopic level. And they showed it off with that demultiplexer thing.
Right.
But there's still a long way to go before we're using this in hospitals or our laptops, right? What I'm still wondering is how they got this control over sound. They just arranged some spheres. How does that do all that?
Well, it comes down to a basic physics thing. Resonance. Remember those spheres in the lattice? Each one has its own natural frequency, like a tiny bell. When a sound wave hits it at the right frequency, it makes the sphere vibrate.
So each sphere is like singing its own note.
Kinda, yeah. And the way they're arranged in that lattice, that affects how all those vibrations interact with each other. That's how they control the ultrasound waves. Think of it like an orchestra. Each instrument plays its part, and the conductor shapes the overall sound.
Okay, so it's like a symphony of sound waves, all controlled by these tiny vibrating spheres.
Exactly. By arranging those spheres in different ways, they can change the tune of the ultrasound, speeding it up, slowing it down, you name it.
So it's not the spheres themselves, it's how they're arranged that matters.
Exactly. Spacing, size of the lattice, the material, it all plays a part.
So it's like a sonic code. Different arrangements make different sounds.
That's a good way to put it. That code is how they design these metamaterials so precisely, making them do very specific things.
All right, I think I'm starting to get it. But before we move on, the MIT researchers said something interesting about how the spheres are arranged. You remember?
You mean the quote from Rachel Sun, one of the lead researchers?
Yeah, that's the one. She said, by placing spherical masses on a spring-like lattice scaffold, we could create direct analogies for how mass affects quasi-static stiffness and dynamic wave velocity. I realized that we could obtain hundreds of different designs and corresponding material properties, regardless of whether we vibrated or slowly compressed the materials.
It's a mouthful, right?
Yeah. So what does it even mean? What's the important part?
Well, it shows how flexible and how much control they have over these metamaterials. Just by moving those spheres around, they can create tons of different materials, each with its own unique properties, all using the same basic building blocks.
So it's like sonic Legos. Build anything you want just by rearranging the pieces.
Exactly. They've built a platform for designing and building all sorts of acoustic metamaterials, each one fine-tuned for a specific purpose. Think about it. Materials that absorb sound, amplify it, bend it, even make it invisible, all just by rearranging those tiny spheres. It's incredible.
All right, I think we covered a ton in this first part of our deep dive. But I got to ask, if we can get this much control over sound, could we really build a computer that runs entirely on sound? Like no electricity, just sound waves doing all the work?
That's the big question, isn't it? And it's one we'll be diving into in the next part of our deep dive. We'll be exploring those challenges and those possibilities of mechanical computing. Can sound really replace electricity? That's what we'll be finding out. So you want to know if sound can really replace electricity and power our computers? That's a big question. To answer it, we need to look at the potential of mechanical computing, but also the roadblocks.
Right, those roadblocks. Like we talked about speed earlier. Can sound waves really keep up with the, crazy fast calculations that our computers do now?
That's definitely a major challenge. Electronic computers, they operate at frequencies like billions of times faster than the acoustic frequencies MIT is using. Catching up to that it's a huge task, but I don't think it's impossible. Researchers are already looking into ways to make those sound waves travel faster within these metamaterials.
So like tweak the material itself so the sound zips around faster.
Yeah, exactly. It's about finding materials that can handle those super high frequencies and then, figuring out how to build those intricate structures with even more precision. But speed's not the only thing, right? Electronic computers, they're really good at being tiny. All those billions of transistors on a tiny chip is why we have our smartphones and laptops and everything.
So how do we make mechanical computing tiny? I mean, sound waves just seem, I don't know, bulkier than electrons on a chip.
It's true, it's a different kind of miniaturization. With these acoustic metamaterials, we're dealing with 3D structures. The MIT research, that's at the microscale, but to get the same complexity as a computer chip, we need to make way denser structures, more intricate arrangements of those spheres in the lattice.
So instead of more transistors on a flat surface, it's like building more complex stuff in 3D, like comparing a skyscraper to a whole city.
That's a great way to think about it. It's not just about shrinking the parts, it's about how everything's connected, how those sound waves move through the whole thing.
Okay, so speed and size. Are there any other, roadblocks?
Well, there's control. Electronic computers, they're incredibly precise. We can control how electrons move to make ones and zeros. How do we get that same level of control with sound waves?
So it's not enough to make them fast and small. You got to be able to manipulate them with the same accuracy we have with electrons.
Yeah, exactly. And that's where those metamaterials are key. The MIT research, it shows that we can already control the speed and direction of sound with a lot of precision just by rearranging those little spheres.
So it's like a sound switchboard, routing those waves along specific paths, kind of like we do with electricity on circuit boards.
Precisely. And the more we learn about these metamaterials, the more we understand how those tiny structures work with sound, the more control we'll have. Maybe someday we'll even be able to control individual phonons, which are like the basic particles of sound.
Wow, controlling sound at the particle level. That's mind-blowing. But even if we can get over all these technical hurdles, do we even need mechanical computing? Our computers are pretty awesome already. Why switch to sound?
That's a good point. Electronic computers have done a lot for us. But they have limits. They use electrons, and electrons can be messed up by, magnetic fields. They get hot, which slows them down and makes them less efficient. And they don't work well in harsh environments like super hot places or high radiation.
So you're saying mechanical computers, they could be tougher, use less energy, and work in places where our electronics just, melt down.
Exactly. Imagine exploring space, working inside nuclear reactors, or even operating inside the human body. Those are places where mechanical computers could really shine. But there's another big reason. New possibilities.
New possibilities, what do you mean?
Well, sound waves, they interact with stuff in ways that electrons don't. They can travel through materials that are opaque to light, they can be focused, bent, they can even give us info about the stuff they travel through.
So we could unlock whole new ways of computing, processing information, new sensors, new ways to interact with the world, all because of how sound works.
You got it. It's like opening up a whole new dimension of possibilities. We're really just at the beginning of what we can do with sound.
This is blowing my mind. Okay, so all these potential applications, from tougher computers to new medical treatment, it's incredible.
Yeah.
But let's come back to MIT. They showed off that acoustic demultiplexer, which was amazing, but it's still pretty simple. How do we go from that to an actual computer?
That's the tough part. We need to figure out how to build way more complex acoustic circuits. Like how to use sound waves to do calculations, like the logic operations we use in computers now. We need acoustic versions of transistors, logic gates, memory, all the stuff that makes a computer work.
So it's not just about controlling sound. It's like designing a whole new blueprint for computing, all based on acoustics.
Exactly. It's a huge challenge, but it's attracting some really brilliant people. There's a growing group of researchers focused on this, and they're making real progress.
So no sound-powered laptops on the shelves anytime soon, but the revolution's starting.
That's a good way to put it. The MIT research, it's a huge step forward. It proves that we can control sound waves with amazing precision on a tiny scale. It's inspiring a whole new generation of scientists and engineers to figure out what mechanical computing can really do. And who knows, maybe someday we'll all have sound-powered smartphones that work underwater, can handle extreme heat, and maybe even diagnose diseases just by listening to the vibrations in our bodies.
That's a future I'd sign up for. But I'm still having trouble picturing how sound waves can do the same complex math as electrons. Can you give us an example, like how this would actually work?
Sure. Let's say we want to build an acoustic adder, something that can add two numbers together using sound.
Hmm.
You could use resonators, each one tuned to a specific frequency, and each frequency represents a different number. You send sound waves with different frequencies through these resonators, and you can make them interact to produce a new frequency that represents the sum of the two input frequencies. It's kind of like a musical instrument, where each note is a number, and you play chords to add them together.
So we're turning math problems into music. That's a
Yeah.
really cool way to think about it. But wouldn't that be, like, super slow compared to our computers now?
It would be slower, yeah, at least for now. But remember, we're just getting started. As we get better at designing and building these systems, we can make them a lot faster.
So speed is a challenge, but not impossible.
Hmm.
What about complexity? Can we build sound circuits that are as complex as our computer chips?
That's what researchers are working on now. One idea is to use 3D printing to create super complex acoustic metamaterials, structures that are like the circuitry on a chip, but for sound. Another idea is to use how sound waves behave, things like interference patterns, to create those logic circuits inside the metamaterials.
So there's a lot of creative problem solving happening in this field. But even if we can build these complex sound circuits, how do we get information in and out of them? We can't just plug in a USB cable, right?
You're right, we need new ways to connect with these sound systems. One option is piezoelectric materials. They can convert vibrations into electrical signals, and the other way around. We could use them to make transducers that can send and receive sound waves, acting as a bridge between sound and electronics.
So we could, like, talk to these sound-powered computers using ultrasound, and they could talk back with electrical signals we can understand.
Exactly. It's a pretty cool possibility, and it shows how we could combine sound and electronics in a seamless way.
This is all so mind-blowing. I'm starting to see how this could really change how we think about computers. But let's make sure we've hit all the important points from the MIT research. What are the key takeaways for our listeners?
All right, so the biggest thing is this research proves we can control sound waves with amazing precision on a tiny scale. We can change their speed, direction, frequency, even their phase. And we do it using these acoustic metamaterials, which are like tiny 3D building blocks for sound. We can build all sorts of complex sonic devices with them, like a toolbox for sculpting sound. Exactly, and the MIT research, it's just a glimpse of what's possible. They built a simple demultiplexer, but we can use these same ideas to build much more complex devices, and that could lead to totally new forms of computing, communication, even sensing.
So, no sound-powered computers in our pockets yet, but this research is paving the way. But I'm curious, what inspired this research? Were they trying to make a new kind of computer, or was it more of a happy accident?
I think it's a little bit of both. Scientists and engineers have always been fascinated by sound, right? But lately, there's been more and more interest in metamaterials, these engineered structures that have properties we don't find in nature. And as people started looking at acoustic metamaterials, they realized that maybe we could use them to control sound in ways we never thought possible. And as they dug deeper, they started seeing the potential for computers, communications, sensors, even medicine.
So, curiosity, ingenuity, and a little bit of luck led to this breakthrough.
You got it. It's a reminder that scientific progress, it often happens when different fields come together. Ideas and techniques from one area can spark something totally new in another.
It's amazing that something as simple as arranging tiny spheres could lead to a revolution in computing. But before we get lost in the future, let's talk about something important. Ethics. If we can control sound waves so precisely, could it be used for, bad things?
That's a really important question. Like any powerful technology, there's always a chance it could be misused. It's super important that we think about the ethics of acoustic metamaterials right from the start, and that we figure out ways to prevent them from being used to harm people.
So we need to be cautious and responsible with this technology, even while we're excited about the possibilities.
Absolutely, we got to make sure it's used for good.
Well said. I think we've covered a lot today. The potential of mechanical computing, those amazing acoustic metamaterials, and the ethical stuff too. But before we move on, I want to leave our listeners with something to think about. If sound can really replace electricity in computers, what kind of world could we build? That's a really big question, isn't it? Like, what would a world with sound-powered computers actually look like? What would change the most?
It's pretty amazing to think about, We're so used to how our electronics work now. They overheat, they get interference, we need big batteries and power cords. What if we could just get rid of all that?
Yeah. Like, imagine computers that are totally silent, super efficient, and they just blend in.
Yeah.
No more noisy fans, no more messy cables. It's just these elegant sound waves, carrying information, doing calculations. But it's not just about the computers themselves, right? It's how we interact with everything.
That's the really interesting part. Right now, we mostly use screens and keyboards and mice, visual and tactile stuff. What if sound was the main way we interacted with technology?
Whoa. Like controlling everything with our voices, getting information through sound cues. That's next level.
It is. And it's not just about us talking to computers either. Imagine if all our devices were connected and talking to each other using sound.
So like buildings that can hear what's going on and adjust the temperature or the lights based on the sounds. Or cars that talk to each other to avoid traffic jams and accidents. Medical devices that listen to our bodies and know when something's wrong.
Exactly. The possibilities are huge, but we gotta be realistic. We're still in the early stages here. There's a lot of work to do before sound-powered computers are everywhere.
Yeah, we talked about the speed thing, making them bigger, more complex. But there are other questions too, right? Like, how do we actually design and program these things? What are the best materials to use? How do we make sure they're reliable and secure?
All good questions, and researchers are working on them. The more we learn about these acoustic metamaterials, how sound works at the tiniest level, the more we'll figure out.
It's going to take a lot of teamwork too, right? Physicists, engineers, computer scientists, even musicians, all working together to create this new world of sound and tech.
Absolutely. It's a really exciting time to be in this field. I really believe we're on the edge of a revolution, something that could change our lives in ways we can't even imagine yet.
But with all this excitement, all this potential, we got to remember the ethical side of things, right? Like we talked about before. If we can control sound so well, we need to make sure it's used for good.
Right. We need to be careful, make sure this technology isn't used for things like surveillance or manipulation or even weapons.
It's a reminder that scientific progress, it needs to be ethical too.
Couldn't agree more. As we explore what we can do with sound and technology, we got to be smart, think ahead, and make sure we're using this knowledge to make the world better.
Well, I think that's a perfect place to wrap up our deep dive into ultrasound metamaterials and the future of computing. It's been a wild ride. From those tiny sonic building blocks to the big picture of a world powered by sound.
It's been great exploring all this with you, and I hope our listeners are feeling inspired and maybe even a little bit mind-blown.
I definitely am. If anyone wants to learn more about this stuff, check out the links in our show notes. We've got links to the MIT research paper, articles about acoustic metamaterials, even some cool videos.
And as always, we love hearing from you. Share your thoughts and questions on social media. Let's keep this conversation going.
That's right. Thanks for joining us on this deep dive. Until next time, keep exploring, keep asking questions, and keep listening for those whispers of innovation all around us. From all of us here at The Deep Dive, goodbye and happy listening.